Again, the homework is due, so please make sure you add yours to the pile before you leave. Again, the solutions are posted in the glass case right outside my office. So we're going to continue and then finish Chapter 2 today. And the first thing that I want to do is talk about the first law. Let me note that last time we really finished up the discussion of properties. We just started looking at heat and work as forms of energy transfer. It's not clear how any of this is going to be used as we begin to solve realistic problems. At this point, we're still just talking about basic concepts, basic terminology. But hopefully, as we go through these next several days, it'll all begin to make more and more sense. And certainly by the end of next week and into the following week, we'll have a better feel for the types of problems that we will be dealing with. So anyway, with this in mind, let's start talking now about the first law. So the first law of thermodynamics. Now, basically, this is nothing more than conservation of energy. That's what the first law of thermodynamics tells us. It simply states that energy cannot be created or destroyed. It can only be transformed from one type to another or transferred from one location to another. But you can't create new energy. You can't get rid of energy. You can just move it around. Now, with this in mind, the basic statement of the first law is that the difference between the energy that we put into the system and the energy we take out of the system is equal to the change in energy of the system itself. That's just a basic statement of the first law of thermodynamics. The difference between what we put in and take out has to represent the change in the energy of that system. Now, if we want to, we could just write it as delta E. We don't necessarily need to write the word system because it's really implied that we're talking about a system. Another thing we can do is you can just write it as E2 minus E1, where basically E2 would represent the final energy and E1 would represent the initial energy associated with our system. So in essence, this tells me that the difference between what goes in and comes out of our system, at least with regards to energy, is equal to the difference between the energy that we end with and the energy that we start with. These numbers can be positive or they can be negative. In other words, we can have more energy in than out or more energy out than in. But this is the basic first law of thermodynamics. Now, let's also remember that we've seen a definition of energy. We know that energy is defined as the energy internal to the system. So this is supposed to be a big capital letter U. In fact, this whole thing is kind of sloppy, isn't it? So the energy, by definition, is the internal energy, and then plus the energy associated with the object's motion and its position in the gravitational field. So plus kinetic energy plus the potential energy. So what we can do then is therefore write that the change in energy is just going to equal the change in the internal energy plus the change in kinetic and potential energies. Or if you will, we can just write this as U2 minus U1. Remember, U is the internal energy. It's a thermodynamic property, so it will have a distinct value at the beginning and at the end of every process. So U2 minus U1. And then the kinetic energy is just 1/2 mv squared. The half doesn't change, nor does the mass. So this would then be written as V2 squared, 1/2 m times V2 squared minus V1 squared. So there's your change in kinetic energy. And then the mass and the gravitational acceleration don't change, so this is just mg and then times the change in position, z2 minus z1. So this is really a more formal statement of the first law of thermodynamics. However, this really just represents the right-hand side of the equation above, right? What about the left-hand side? What about the E in minus E out? So what we can do is we would note that this E in and E out, these represent the transfers of energy, okay? And we'll also note then that E in minus E out can really come from just three possibilities, right? We can have some energy transfer based upon work that's being done. So I'll have a work term here. I'll fill it in just a moment. We also have the possibility of transferring energy by heat, right? So we're going to have a heat term here. Well, I'll write out the word heat. Okay. And then there's also the possibility of energy being transferred due to flow. You could have mass that's flowing in with a certain amount of energy and mass that's flowing out with a certain amount of energy. So we'll also write flow here. So basically we'll write this then. So this says but. So the difference between the energy in and out, and again we're looking at the left-hand side of that equation above, this is the difference between the work that goes in and out. So I'll put a work in minus work out. And then the heat that's going in or out, so I'll put a Q in minus the Q that goes out. And then there's going to be the possibility of flow. So I'll just put the energy that flows in minus the energy that flows out. So this is just a big general equation, but you can see that these two equations, the last two big equations that are written here, basically have to be equal to each other, right? The delta E is the difference between E in and E out. So these two, these are equal. Right? Just two different ways of writing the same thing, right? Do we think of the energy in terms of the work, the heat, the flow of energy in and out, or do we think of it in terms of the changes to that system with regards to its internal energy or its kinetic or potential energy? So this, I could just write it as one big long equation. I could say that this first equation equals this second equation, but again, that's just understood. So what I would like to do is note one more thing here. Remember we talked about the sign conventions for our heat and our work term last time. In some books, you don't actually see it written this way with a separate work in and out term, a separate heat in and heat out term. Typically, we would just have a minus W, and W would represent the work. If the work was work out of the system, that's work being done by the system to its surroundings, so that would be considered a positive term. If work is being done to the system by the surroundings, that would be considered a negative term. The heat transfer term we'll sometimes just write as a Q. If there's heat added, then there's a positive heat term. If there's heat rejected, then there would be a negative heat out term. And then we could just say plus delta E for flow. Now, quite frankly, different problems may or may not have work or heat or energy flow terms. It's really just going to depend upon the problem at hand. So what I want to do, and this is really just to help us think about the nature of work and heat transfer and its relationship to energy. Let's do an example problem. And now I would like Michaela, please, to switch over the computer to one of these screens. So the first example I'm going to do is actually the example 2-39 from your textbook. So she's working on it. We're getting closer. Okay. All right. So let's see. I might have to. Okay. So this is the example problem. All right, so with regards to this particular example problem, again, this is 239. And this actually comes from your edition, the 8th edition of your book. So basically it says you have water that's being heated in a closed pan on top of the range, which is an old-fashioned word for stovetop, while being stirred by a paddle wheel. Okay? During this process, 30 kilojoules of heat is transferred to the water. Additionally, 5 kilojoules of heat is lost to the surrounding air, and paddle wheel work, which amounts to 500 Newton meters, is being done during this process. So just think of the paddle wheel as you with the spoon kind of stirring, right? And it says determine the final energy of the system if its initial energy is 10 kilojoules. So the first thing I like to do as we start a problem like this is just make my own drawing. You can certainly use the drawing that's there, but I'll just show it as a big square. So that's my pan of water. It does say water, so I'm going to put a little H2O in here. And then it says 30 kilojoules of heat is transferred to the water. So there's going to be some Q in of 30 kilojoules. It also says that 5 kilojoules is lost to the surroundings. So there's also going to be a certain amount of Q out of 5 kilojoules. And then there's this paddle wheel, so I'll just show a little paddle wheel in there. And a paddle wheel is a device that does work to the system, right? The water is not causing the paddle wheel to rotate. You're holding on to that paddle wheel, your big spoon, if you will. So there's a certain amount of work in this particular problem, and that amounts to 500 Newton meters. Okay. And they also tell us in this particular problem that the initial energy is E1, and that's given as 10 kilojoules, and we want to find the final energy E2, which is my unknown. Okay. So I always like to start any problem in this fashion. You know, you can cut and paste or take a photograph if you want and photo it onto a clean piece of paper, and then you don't have to write it all by hand. Of course, in class, it's all on the board. All right, so what do we do in this problem? Well, we just have to think about which equation applies, and basically the equation is the one that we just finished looking at. So delta E, which is the difference between the final and the initial energy, is going to equal the difference between the heat in and out and the work in and out and the flow in and out. Okay, so here a lot of these terms are simply going to go away. There is no work output, right? So we'll just show that as 0. There's no flow at all. I mean, it's just a container of water sitting on top of the stove, so there's no flow. So we can just easily show those as both being 0. And then the other terms are all terms that we have. So E2 is my unknown. E1 is 10 kilojoules, so minus 10 kilojoules. Q in is 30 kilojoules minus the heat out, which is minus 5 kilojoules. And then the work in is 500 Newton meters. Now let's keep in mind that a Newton meter is the same as a joule, and that there's 10 to the minus third kilojoules per joule, or if you will, 1,000 joules per kilojoule. So that actually takes care of the units in that first work term, and then I'll just put minus 0 plus 0. So the problem's essentially done, right? It's just a matter of going through the mathematics. We end up with E2, and let's see, the 10 goes over to the right-hand side, and then we have a 25 kilojoules, and then we have a plus, and this is 0.5 kilojoules. So basically E2 is just 35.5. Now, there will be a time in the future where we're going to try to find out a little bit more about the nature of that water. What is its temperature, what is its pressure, what is its specific volume or density, if you will. But we're not near ready to do that yet. For now, we're just trying to think about energy. So this just allows us to look at one pretty simple, straightforward problem and think about the energy that's involved. So are there any questions on this problem? Yeah.
So in the book it says that it's E in minus E out. So
Yeah.
in this problem, we're saying that E in is the 10 kilojoules, or the E out is the 10?
No. The delta E is the difference between the energy in and energy out, but it's also the difference between the energy we end up with, E2, and the energy we begin with, E1. So, kind of think about the left-hand side versus right-hand side. In this particular equation, the left-hand side represents the change in the system's energy, the difference between what we end with and what we start with. The right-hand side represents the various flows, whether it's heat or work or some other form of energy flow. So, in this case, E2 is simply the final energy contained within the water of that system. Okay, yeah.
Last lecture you said that the work and heat are like kind of opposite in definition. You add heat to a system, it's positive.
Right. In fact, let me do this. If I wanted to solve it slightly differently, I could say E2 minus E1 equals Q minus W plus delta E that flows. Okay, I changed the order on the previous page. It had a minus W plus a Q. But this would be the proper formulation. Now, let's think about it. If heat is added, it's a positive. So we're adding 25 kilojoules. But heat is also being rejected. So that's, by our sign convention, a negative. So we would add to it minus 5 kilojoules. So that's just your heat term. Now, what about the work term? Work is being added to the system, which makes it a negative work, right? Not work done by the system, but work done to the system. We already saw that was equivalent to 0.5 kilojoules. But since it's being added to, it's a negative number. So we have a minus 0.5 kilojoules. And then there is no energy that flows, so just plus 0 again. So you get exactly the same thing. You have E2 minus 10 kilojoules equals, and then what would this be? This would be 20 plus a 0.5, and therefore E2 is still going to be 35.5 kilojoules. Okay, so when we start getting into problems of more significance, I'm going to use this upper version, E2 minus E1 equals Q minus W, and I will just simply let the sign convention do its thing. Positive Q is heat added. Positive work is work out, if you will, being done by the system. Work in is a negative. And as long as we're consistent to our sign convention and consistent to the equation, that the equation definitely has a minus sign in it, then we'll always be able to get the right answer. Anyway, just another way of writing the same problem. Any other questions? Okay, let's look at another. Okay. So this one is also out of your textbook, and it's problem 247. Okay. So in this particular problem, it's similar but different, right? This says that we have a room that initially is at the outdoor temperature of 20 degrees Celsius. There's a 40-watt light bulb, a 110-watt TV set, a 300-watt refrigerator, and a 1,200-watt iron. Assuming no heat transfer through the walls, determine the rate of increase of energy content of the room when all these electric devices are on. Okay, so this one is a little bit different. First of all, if you look at the wording and look at the units, everything's in terms of a rate, right? Watts is joules per second, right? It's energy per unit time. They're talking about the rate of increase of energy content of the room. So how might we approach that problem? Well, we're going to start with the same basic equation, in that delta E is going to equal, the difference between the heat transfer and the work. And then also, the flow. So that basic equation doesn't change. However, what we really want to do is look at this as a rate equation. Why not? Why don't we just take the time derivative of the whole thing? So if we do that, if we just take that time derivative, then basically we're going to get E dot, in other words, the rate change of the energy of the system. And in fact, isn't that what they've asked us to find in this problem? And then here, we're going to have rates of heat transfer work. So we'll have the rate of Q in. Remember, we saw the notation last time. A dot is a time derivative, right? It's per unit time. So there's a rate that heat is being added. This should be a minus sign. There's a rate that heat is being rejected. There's the rate that work is being done to the system. There's a rate that work is being done by the system. And then we'll have the rate that energy flows in and flows out. Okay. Now, we also want to show this room. So there's the room. It tells us that the initial temperature is 20 degrees Celsius, but we really don't have to use that for anything. We're not yet to the point, like the point I made in the last problem, to actually solve problems where we're interested in the relationship between various properties. We're just not there yet. But we certainly understand that there's going to be all these different devices, right? If we have lights, then all the energy that that lighting system uses eventually is going to be transferred into the room. We can think of this as a form of electrical work. You could also think of it in terms of heat. We also have this 110 watt TV set. I mean, ultimately, the energy being used by that TV set will dissipate as a form of electrical work into the room itself. In fact, everything works that way. If we have the refrigerator, actually, the 300 watts from that refrigerator is being used by the compressor of the refrigerator. So that's an actual work input, even though it doesn't specifically say it. But I mean, that's what works on a refrigerator. It's the compressor that requires all that energy. And then you have the iron. And one could argue, well, irons, they just get hot, right? So we can think of it as electrical work, or we can think of it as heat transfer. Any way you look at it, there's energy coming off these devices which will remain entirely within that room. You can think about it as if these were heat transfer terms. You can think about it as if they were work terms. It really doesn't matter. You can also think about them as energy flows. It's kind of unclear how one deals with electrical problems like this. Frankly, though, to be consistent with the book, I like to think of these as electrical work. Even though ultimately that work through friction dissipates as heat into the room, they're still electrical forms of work. So we basically have four. Yeah, thank you.
Delta E dot, right?
Yeah.
Yeah, it should really be. Although sometimes having a delta and a dot in the same equation doesn't always make a lot of sense. But yeah, we can think of it as delta E dot, the rate change in the energy. Either way is fine. Okay. Anyway, so let's identify what we know. We have a certain amount of work in based on the lights and based on the TV. So let's see, we have 110 watt lighting. No, that's not right. 40 watt lighting, 110 watt TV. So 40 watt light, 110 watt television. We also have the refrigerator, which is 300 watts. So 300 watts. And then we have the energy in associated with the iron, which is what, 1200 watts. Okay. So all we really have to do is add everything together and neglect the terms that are to be neglected. There is no heat transfer per se coming in. There's no heat transfer going out. We'll assume that the walls are well insulated and we've got no losses that way. There's no work being done by the room. It's all being done to the room. So the work out is 0. And then there's no flow. Nothing flows in or out. So those are all 0. So ultimately, we would basically just have that the delta E dot is going to equal the summation over all these W dot in terms. So it's just a matter of adding everything together. 40 plus 110 plus 300 plus 1200. They all have the same units of watts. So basically 1650 watts. Okay. So that's the rate at which the energy is changing within this particular room. Okay, so again, just to get you thinking about the nature of heat transfer and work, these are not particularly complicated problems here in this part of Chapter 2. So are there any questions on this one? Yeah.
On the last example, when you ran through it the second time, it didn't add up to 35.
Really? Oh, yeah. Right, it was my mistake. Yeah, this should have said 35, right? I'm sorry, it should have said 30. So 30 kilojoules coming in plus the 5 that goes out. I guess that's where I came up with the 25 number. But yeah, this should have said 30, and then this should say 25 right here. And then it adds up appropriately. Yeah, so yeah, fix those two typos if you would. All right, so again, any other questions? All right, there's one other topic that's covered here in Chapter 2, so let me just discuss it very briefly. And this has to do with what's called efficiency, or more specifically, energy conversion efficiency. Okay, so I think this is section 2.7, I think. Anyway, what is meant by energy conversion efficiency? Okay. So first of all, the energy conversion efficiency is just given the Greek letter eta. Eta is always the term we use for efficiency. And we're going to define this energy conversion efficiency as follows. It's the desired output divided by the required input. Okay. Now, there's different efficiencies that we're going to use as we study different types of devices. Most of the time we're going to be dealing with what are called steady flow devices. So these are the devices I mentioned last week, like pumps, compressors, turbines, devices that involve some sort of flow. We need to understand that the energy change associated with the fluid that's moving through these devices is not going to be exactly equal to the mechanical energy that goes into or out of those devices. So for instance, let's say that I had a pump, just to give you two examples. First of all, I'd use eta with the subscript P, P for pump. Now, a pump is a device that moves a fluid along, right? And in the ideal world, however much mechanical energy we give to that pump from our electric motor to get that pump spinning, all of that energy should go to the fluid itself, right? But it doesn't work out that way. In the real world, there's going to be losses, primarily due to friction, because there's going to be bearings in the motor and bearings in the pump, and there's going to be surfaces like the inside of the rotating part of the pump. The impeller might actually rub against the inside of the casing of the pump a little bit. So you're definitely going to have frictional losses associated with these systems. So the fact is that the energy increase of the fluid and that's our desired output, right? We're trying to move a fluid along. That energy input of the fluid is not going to be as great as the mechanical energy input that goes into that pump, presumably from the electric motor. We know that there's going to be losses, and this is always going to be less than 1.0, or if you will, less than 100%. So at some point, we're going to start talking about efficiency in this class. We're not going to do it yet, but it is something you want to be thinking about. When we look, for instance, at that last example problem, the implication there is that that house was ideal, that the insulation on that house was absolutely perfect, and that all the energy released into that room is going to stay in that room. Nonsense, right? In the real world, you have losses. There are efficiencies associated with processes, and we're not going to be able to get to that now, and that's going to come when we get to Chapter 7, but at least think about it, that there are idealized problems that we're going to be learning about before we start looking at some more realistic problems. What about a turbine, just as another example to get you thinking? So first of all, we use the subscript T for a turbine. So what is your desired output from a turbine? Well, it's some sort of mechanical energy output. It's rotation on the shaft of that turbine because that's spinning an electric generator. So basically, it's mechanical energy output, that is our desired output. That's the rotation on the shaft of that electric generator. But what is the required input? Well, it's a fluid, right? It's like high pressure, high temperature steam that's coming in at certain conditions. It's giving up energy, causing rotation, and then it's coming out at lesser conditions. So the denominator is the energy decrease of the fluid. But again, there's losses, right? There's always got to be friction. The actual mechanical output of that turbine and the electric generator is definitely going to be less than the change in the energy of the fluid that moved through that turbine. So this is the real world for us. And again, this is not something we're going to be talking about now, but it's something we want to be thinking about for the future. So once again, this has to be less than 100% or less than 1.0. And I'll just note covered in chapter 7, which is still like a month and a half away. So don't worry about it for now. But it is discussed in chapter 2, so I wanted to at least bring it up now. Yeah.
Is fission the only one that can be above 1.0, or
Say that again?
fission? Can that be above 1?
You said fission?
Yeah, fission.
Like nuclear fission?
Yeah.
No, nothing is ever above 1.0. No. You have to think about a fission problem differently. Fission problems would not be simple compressible systems. We're only dealing with these simple compressible systems. You talk about nuclear fission, you're talking about taking subatomic particles and breaking them. Well, I'm sorry, you're taking a large nucleus and you're breaking it into its smaller particles. And that's a nuclear reaction, and that's by no means a simple compressible system. So we're not ever going to be talking about that in this class, but it is something you want to think about. But it's well beyond what we'll be dealing with. Anyway, real processes always have efficiencies less than 1, right? There's always a loss. There's always something you have to pay for. We'll get into this with regards to the second law of thermodynamics, and it's good to understand efficiency because this allows us to compare different processes. If we have 2 pumps and one is 80% efficient, the other is 85% efficient, you want to buy the 85% efficient pump because for less energy input, you're going to get the same amount of fluid pressure increase. Same thing with the turbine. Why not buy the turbine that operates at 35% instead of 30%, something like that? More efficiency gives you a greater output that you desire. Again, something to think about for the future. So, yeah.
So when you say energy decrease of the fluid, could you also say do you mean that the energy of the fluid that's going and not all of it is gonna eat into the output, right?
Well, right, but that's 2 different things. When we, let's say, run steam through a steam turbine, it's going to come out at a lower pressure and temperature. It will have a lower amount of energy associated with it. That's for sure. I'm just saying, with regards to the definition of efficiency, that change is still not going to be equal to the amount of electricity that's produced as rotation on that shaft. So certainly we can improve the overall performance of a system by dropping the pressure and temperature of that steam as much as possible as we move through the turbine. But that's not really what I'm referring to when I talk about efficiency here. Okay. All right, so let's move on. And we're actually beginning chapter 3 now. By the way, I'm done with the example, so that's the only other example I have for today. So now we're going to talk about pure substances. Okay. So we understand a little bit about the concept of properties and of thermodynamic states. We understand that things like pressure and temperature and specific volume are intensive properties, and they're important properties for us because they're measurable, and it's easy for us to relate measurable properties to one another. Keep in mind, too, that when we talk about a pure substance, we're talking about something that's homogeneous. Okay, so as you look at it, it looks the same. Every bit of it looks the same. That's a homogeneous substance. Think of that as a well-mixed substance. But also we would note that there's no change in chemical composition. So there's no chemical reactions taking place. If we start with H2O as water, we end with H2O as water. I mean, that's it. We're not undergoing any kind of a process where the water is going to turn into hydrogen and oxygen. We're talking about pure substances. They're homogeneous. They don't change chemical compositions. All right, so that's what we're talking about. We're always going to be talking about pure substances in this class, things like water or maybe a particular refrigerant that's used commonly in refrigerators and freezers and air conditions. Now, another thing that should be noted is that all pure substances have phases. And I think we already know what these phases are, right? We know that a substance can either be a liquid, or it can be a solid, or it can be a vapor. Sometimes in some thermo books you'll see the word fluid instead of liquid. Sometimes you'll see the word gas instead of vapor, but they mean exactly the same thing. Okay? So these are the three phases that we know naturally exist. Now what I want to do is I would try to explain to you the way these phases exist and occur in the real world of ours. So let's just look at an example. That's probably the easiest way to do this. Let's say that we have a closed system in other words, we have a closed system, meaning that nothing gets in or out, right? It's of a fixed mass. So let's consider a closed system, and again, of fixed mass. And let's assume that it's at constant pressure. So, for instance, maybe you just have a bag. You have something inside that bag in the atmosphere. Its pressure is always going to be at atmospheric pressure. Or you could also think of it as a vertical, frictionless piston cylinder device. Okay. In either case, we're looking at something that has a constant pressure. Now, what is this whole vertical piston cylinder device? You'll read about this a lot. This is just one very common device which maintains a constant pressure. It's a closed system, so we have a cylinder, and that cylinder has a piston on top of it. Presumably, it makes a nice tight seal, so no mass can get in or out. Also, presumably, that piston has a fixed weight or a fixed mass associated with it. So as long as that is frictionless, in other words, that piston is free to move up and down, it's always maintaining constant pressure inside that cylinder. It has to, right? There's going to be a certain amount of atmospheric pressure pushing down on the piston. There's going to be a certain amount of weight, which is not changing, pushing down on the piston. So basically, you have a fixed area, you have a fixed force above it, so the pressure has to remain constant. So whenever you see the words vertical frictionless piston cylinder device, that's one of these kind of devices here. So we're going to consider this closed system at a constant pressure, whether you think about it as a bag or you just think about it as a piston cylinder device, either one is fine. And then let's just say that it contains water at minus 10 degrees Celsius. And let's just say that that fixed pressure is 1 atmosphere. So 1 atmosphere is what? That's the same as 101.3 kilopascals. Okay, so that's the constant pressure being maintained. Now what I want to do is consider what phase this is going to be. Well, we all know the answer, right? We know that at standard atmospheric pressure, if the temperature is less than 0 degrees Celsius and it contains H2O, it's got to be solid water, right? So the phase is solid. In fact, we have a special name for solid water. We call it ice. Okay, so that's something that's pretty clear, right? At one particular temperature and pressure, at atmospheric pressure, at negative 10 degrees Celsius, clearly we have ice. Okay, now let's do something to it. Let's add heat. Okay, so as we add heat, the pressure remains constant, but that doesn't mean that the temperature remains constant. We've all added heat to ice before. Just let an ice cube sit out on the countertop, and we know what happens, right? it eventually is going to melt. But it's not going to melt immediately. First, as we add heat, the temperature rises until it finally gets to 0 degrees Celsius, right? And it's only after the temperature gets above 0 degrees Celsius will the melting process begin, okay? In other words, the phase change begins. We're going to begin to go from a solid to a liquid, okay? So at 0 degrees C, the solid to liquid phase change occurs. In fact, we say that at 0 degrees Celsius, the solid and the liquid are actually in equilibrium. Okay, they both exist simultaneously at 0 degrees Celsius. Now, this is something you may not be aware of. Some people have this inaccurate impression of the way that substances work. Some people think that when you get up to just barely below 0 degrees Celsius, we're ice, but just the moment we get up to 0, or maybe just a tiny fraction above, then it instantly changes into liquid water. It doesn't work that way, okay? You go all the way up to 0 degrees, and at exactly 0 degrees, the phase change begins. You will have part liquid and part solid water, and you'll still be at 0 degrees Celsius. It's not until you get past 0 degrees Celsius that all the water has melted, that is, all the ice has melted, and you actually have liquid water finally. So we need to understand that at 0 degrees, we have a solid-liquid phase change, and it takes time. And heat. You add a little bit of heat, some of the ice is going to melt. You add more heat, the rest of the ice is going to melt. So it takes time and heat for this to occur. In the meantime, we say that the solid and the liquid are in equilibrium. Okay. Now, we continue adding heat. Eventually, all of the solid ice will melt. So, okay. So, keep adding heat. Finally, only liquid remains, but it's still at 0 degrees Celsius. Okay. We now have to add even more heat, and then as we add more heat, finally we'll be able to increase the temperature. Okay. So add more heat, and what's the next thing that's going to happen? Well, we're going to have to wait until we get all the way up to 100 degrees Celsius, and now we have another phase change. Now the liquid water is going to turn into water vapor, which we also call steam, right? So we add more heat, the temperature rises to 100 degrees Celsius, and now the water begins to vaporize. Or if you want, you can use the word boil, you can use the word evaporate. It all means the same. So the water begins to vaporize at 100 degrees Celsius. But it's not any different than what it was with ice, right? It's not like we get almost to 100 degrees and we have liquid water, and then above 100 degrees, it's water vapor. No. You're going to keep increasing in temperature until you get exactly to 100 degrees Celsius. And then at 100 degrees Celsius, you remain while you continue to add heat. And more that water finally boils into water vapor. Okay? So water begins to vaporize at 100 degrees C. Finally, enough heat is added such that all the water is a vapor, okay? And then it's after that, only after all the water has boiled into water vapor, only then can the temperature start to rise again. So if we add more heat, basically causes the temperature to rise, well, to rise more. So that's what happens, at least to water at atmospheric pressure. Okay? Now, you might think about this and say, well, is that the only thing that could happen to a pure substance? I mean, we are talking about pure substances. I used water as an example. Does pretty much every pure substance do the same thing? Does it boil at 100 degrees Celsius? Does it freeze at 0? Well, the answer is both yes and no. Certainly all substances are going to have similar behavior, but it's not going to be at the same temperatures and pressures. Let me just give you another example. How about carbon dioxide? So here's another example. What happens if you have carbon dioxide at 1 atmosphere, and I don't know, let's just say that it's at 0 degrees Celsius. It's a gas, isn't it? Even at that cold temperature, carbon dioxide at atmospheric pressure is going to be a gas. You have to bring it all the way down, gosh, I don't have the number, I think it's like minus 40 degrees Celsius or something like that before it's actually solidified. So if we have very, very cold carbon dioxide, it's in solid form. In fact, we call it dry ice, right? Dry ice is nothing but solid carbon dioxide. Now, what happens when you heat up dry ice? If you heat up dry ice, do you first end up with like a little pool of carbon dioxide, and then after a while that pool vaporizes into a gas? No, it doesn't work that way, does it? It turns out that for carbon dioxide, if we cool it below 0, it's going to turn directly from a vapor into a solid, or in the way you usually see it, when you buy it, it's usually a solid, and it's going to change directly into a vapor. There is no melting process for carbon dioxide. So CO2 behaves a little bit different than water, doesn't it? Or does it? Let's see. So let's say we have CO2 at 1 atmosphere. Let's change this. Let's say that it's at minus 50 degrees Celsius, and it's going to be a solid. Okay. As we add heat, it will eventually reach a temperature at which the solid, it doesn't actually melt. The process is called sublimation, or we could say it sublimes. The solid sublimates directly into a vapor. How weird is that? But that's what happens to it. Now, the funny thing is this. Water will do the same thing, just not at atmospheric pressure. You'd have to go to a very low pressure before you'll find that water behaves the same way. But it will occur that way. So what I'd like to do at this point is put a drawing on the board. If I were to, let's say, just plot pressure versus temperature for any pure substance, I will be able to notice definite regions. Okay. I would notice a pattern that looks like this. So I would just take data. I mean, I'm not inventing anything here. I would just take data for any pure substance. What I would find is that at the lowest temperatures over a wide range of pressures, I could be in the solid phase. At the highest temperatures over a wide range of pressures, I could be in the vapor phase. But in order for me to be a liquid, I actually have to be at a pretty high pressure. I have to be up here somewhere. And this is what we find for every pure substance. The units are the only thing that varies. When I was talking about carbon dioxide was down here, right? This would have been atmospheric pressure down here, and you would see that the solid carbon dioxide, the dry ice, once you give it enough heat, would finally get to a temperature where it would then directly turn into a vapor, this whole sublimation process, right? On the other hand, if I have something like water, then atmospheric pressure for water would be up here somewhere, right? Water at atmospheric pressure would drop down, would change phase, well, we know at 0 degrees Celsius into a liquid, and then that liquid is going to turn into a vapor when we get up to 100 degrees Celsius. If we go into the mountains, it's different, right? We know that water boils at a lower temperature in the mountains. When we're up in the mountains, our atmospheric pressure is a little bit lower. In fact, what happens is that ice forms at a higher temperature. You can see that drop in the pressure, you go up into the mountains, right? Ice forms at a slightly higher temperature. Therefore, your cold drink, when you put an ice cube in it, isn't as cold as it is down here at sea level. And on the other hand, water changes into a vapor at a lower temperature. So you're going to boil your spaghetti at like 180 degrees Fahrenheit, or let's call it 90 degrees Celsius, instead of 100 degrees Celsius, and it takes longer for you to cook it. So this is how the real world looks. Every substance has a diagram that looks like this one. It just so happens that this is how water would behave at atmospheric pressure. Down here, this is how carbon dioxide would behave at atmospheric pressure. If you went up to a high enough pressure, then you would find that carbon dioxide as a solid would actually melt into a liquid. And then if you continue to add heat at that elevated pressure, it will indeed turn from a liquid into a vapor. So that's how pure substances work. Let me identify some points here. This big dot right there, right in the middle, is called the triple point. The triple point is where the solid and the liquid and the vapor phases all exist in equilibrium. There's only one single point, but if you happen to have any pure substance at exactly the pressure and temperature of that triple point, then you will have all three phases that exist simultaneously. So that's the triple point. The three phases exist together in equilibrium. Okay. This line down here at the bottom, we would just call this the sublimation line. This line over here on the right-hand side is our vaporization line. And then this line over here, where the liquid and the solid can be in equilibrium, that's what we call the fusion line. Okay. And then there's one other point to show here. At the very top on this, the vaporization line, this is called the critical point. It turns out that us human beings can see a distinction between liquids and vapors. But when you get to a high enough pressure, you have what's often just called the supercritical fluid. If you're above that critical point, there is no visible distinction between liquid and vapor anymore. It almost looks like a marbled substance. It's very, very hard to describe. But I'm sure if you go online, you can find some images or even videos of supercritical fluid. But nonetheless, this critical point is also a very important point for us to recognize. Right? So there's data for a lot of these different points. For instance, if you go into table A1 of your textbook, it gives you data for like critical point. So there's some data in table A1. And by the way, there's also table A1E, which would be the English unit. So I'm not going to keep saying A1 or A1E. I'll talk about table A1, but E would be the table for English units. Anyway, there's going to be data in table A1 that's going to give you some of this information. Not all of it that you need, but some of it. We will talk about our data tables here in a lot of depth here over the next couple of days. Now, there's a little bit of a problem with this pressure temperature diagram. The fact is that for most processes that we're interested in the real world, in the industrial world of ours, are not problems that involve a fusion process or a sublimation process. We have very few industrial processes where we need to worry about a solid that turns directly into a vapor, or any industrial processes where a solid turns into a liquid. In fact, we rarely concern ourselves with solids. The problem with solids is that they don't flow well, and they're very rigid. So how could you really use them in any kind of industrial process? We need gases that move easily. We need liquids that move easily, that allow us to transfer heat easily, that allow us to do work on them easily. So the vast majority of the problems that we deal with are actually problems in this region. I'll just draw a big cloud here. Okay, the region in and around the vaporization line and the critical point. Okay, so it's this cloud that's the most useful area. Okay, it's most useful. So what I want to do is make a new drawing, a new set of drawings, which is going to actually be the drawing that we're going to use like 99% of the time as we illustrate processes. And that will be the temperature volume diagram. By the way, in case it isn't obvious, just because the pressure and temperature are in equilibrium doesn't mean that the other thermodynamic properties are going to remain the same as well. We know that when water boils from a liquid to a vapor, sure, the temperature and the pressure are steady, but the volume changes significantly, right? 1 pound of water is, what, about a pint, right? But 1 pound of steam, at least at atmospheric pressure, would be about 1,000 pints. There's a huge difference in the specific volume, the density, if you will. So that's really what I want to illustrate on this next set of diagrams, not just because I'm interested in this region. I'm also specifically interested in how the intensive property that we call specific volume varies. So let's make a new diagram from the old diagram. And this will be as follows. This is going to be a temperature versus specific volume diagram. Okay. Now, in the temperature versus specific volume diagram, I still want to show that vaporization line, but it's not a line anymore, is it? The specific volume of the liquid right as we get to that vaporization line is going to be a whole lot smaller than the specific volume of the vapor once we pass across that vaporization line. So when we look at this, what we really want to show is a diagram that would look like this, that would have a dome on it. Okay? And this entire dome represents just that single vaporization line. We give this a special name. This is called the saturation region. This is a region where we have a mixture of part liquid and part vapor. Okay? So that's called the saturation region. The critical point is right at the top. Okay? Anything to the right of the critical point and to the right of the right-hand side of the dome here, this is going to be our vapor. Now, actually, we have two different words to describe vapor. If we're right on this line, that is, if we're still right on the vaporization line, but we're still all vapor. In other words, the last drop of water has finally turned into a vapor, but we're still at 100 degrees Celsius at standard atmospheric pressure. Well, that's what this line represents. So in order to make a distinction between that line, which is a vapor, and anything to the right of that line, which is also a vapor, we give it a special name. So we use the word superheated vapor to represent anything to the right of the dome. And if we're actually right on the dome, then this is called a saturated vapor. So the saturation region is a mixture of part saturated vapor and then part saturated liquid. So we're going to do the same thing over here on the left-hand side. When we just barely get to the point where the liquid water is just beginning to vaporize, we're at exactly 100 degrees Celsius, 1 atmosphere, yet we're still all liquid water. We call that a saturated liquid. Now, anything to the left of the saturated liquid is still a liquid, but again, we want to use terminology so we can make a distinction between the two. We use the word compressed liquid or subcooled liquid to talk about a liquid that's beyond the saturation line here. So again, we call this either a compressed liquid or subcooled liquid. Either phrase would be just fine. Okay. If we're interested in solids, not the right diagram. Solids would be like way down here somewhere. If we're interested in supercritical fluids, we'll be way up here somewhere. We typically aren't, right? We're typically interested in phase change. Now, if you think about it, those two huge systems that I mentioned the first day of class, like a steam power plant or a refrigeration system, this is exactly that, right? In a steam power plant, we boil water into steam, and then we condense the steam back into liquid water. In a refrigeration cycle, we're going to evaporate a refrigerant, Freon, if you prefer that word. We'll evaporate it from a liquid into a vapor, and then we're going to condense it from a vapor back into a liquid. So this is definitely the region that's of primary interest to us. And then one last thing to note, when we talk about the saturation region, we can also call this simply the two-phase region. Okay, usually we just use the word saturation region. So when we're trying to describe a substance, more often than not, we're going to be on this diagram somewhere, and we should be able to get data based on the information in this diagram. Okay. Now, let me make another comment. If we are in the superheated vapor or the compressed liquid region, we're no longer on that vaporization line, right? We're to the left of it, to the right of it. As such, pressure and temperature are independent properties. And if we know if we know both pressure and temperature, then all other properties are known, right? Pressure and temperature are both intensive properties. They don't depend upon the quantity, and they're both independent as long as we're outside of this saturation region. So for a compressed liquid or a superheated vapor, pressure and temperature are independent and intensive properties. The key here is that they're independent. But what about in the saturation region? So for a saturated mixture, as we'll call it, which we can also call a two-phase mixture. But for a saturated mixture, pressure and temperature are still intensive properties, but they're not independent anymore. Think about it, right? I just gave you those two examples, one for water, one for CO2. At atmospheric pressure, the phase change from a liquid to a vapor occurs at exactly 100 degrees Celsius, and it never changes. As long as atmospheric pressure is 1 atmosphere and you have a phase change taking place, you have to have a temperature of exactly 100 degrees Celsius. No ifs, ands, or buts, right? That's exactly the way it is. But for a saturated mixture, that means that since pressure and temperature are not independent, we need another property in order to determine the thermodynamic state. So whereas for a compressed liquid or superheated vapor, P and T are independent intensive properties and therefore determine the state, for a saturated mixture, pressure and temperature are not independent. Okay? In other words, we need pressure or temperature and one other intensive property to set the state. Now, when I say set the state, that's just another way of me saying we know all the other thermodynamic properties, right? If we have any two independent intensive properties, we can find all the rest. In other words, we've set the thermodynamic state. Everything else is known to us. Now, the question now is, what is that one other intensive property that we need? It really depends upon the problem. In many problems, it's the specific volume, right? I mean, note that this is a temperature versus specific volume diagram. I didn't just write this here by accident. Turns out the specific volume, being just the ratio of volume over mass, is measurable, right? We can very easily find a substance's density, or if you will, its specific volume, the inverse of density, right? So more often than not, we need pressure or temperature and one other intensive property. Usually it is the specific volume. Which is lowercase letter v. Okay. Now, that's not the only other property. There's another property which I will just introduce you to today. And this other property, let's call it a new property. It's called quality. And quality is just given the lowercase letter x. Now, quality is defined in a very simple fashion. It's defined as the vapor mass over the total mass in a saturated mixture. Okay. Now, if you think about it, we know that if we have a two-phase, or what we call a saturated mixture, it's only going to be a mixture of liquid and vapor. It turns out that that vapor fraction is what we call quality. I mean, this is actually a historic term. If you think about, let's say, the boilers that were made in the late 1800s, they weren't perfect devices. It was hard to turn all the water into steam. You were lucky if 95, 96, 97% of the water actually changed phase into steam. That's the quality, right? If you got 95% of that water changing into steam, then that told you that the quality was 95%, and that's where the phrase quality comes from. So just think of your quality as a measure of how good a job your boiler did at turning liquid water into water vapor. More specifically, it's just the fraction of the fraction of water vapor over the total mass. Now, it's not just for water, right? Water is an example. Any pure substance that goes through a phase change will have a quality associated with it. Nonetheless, this is really all the time that I have today. So we'll continue this next time. We'll talk more about quality. We'll look more at thermodynamic property diagrams. And I'm also going to introduce you to the property tables that are in your book. So if you want to follow along, bring your textbook or maybe bring the printout. If you have a printout of some of the appendix pages, mainly we're going to be looking at like A4 through about A13 in the appendix next time. I've got them on a slide, so I will put them on the board, but if you want to follow along, bring your book or your property tables with you next time. Anyway, that's all for today. Please don't forget to turn in the homework that's due. The solutions were posted already right before I came to class, so look at them outside my office. My intention is to have these graded and back to you before Friday, so I'll just give them back to you then. Okay, see you guys Friday.